You may want to settle into a comfy chair, get a snack, because 4.3 is a fairly long section. We are going to try and get every little bit of information out of the derivative as we can. So we're going to be looking at the first derivative, the second derivative, what do these tell us, what does that look like graphically, how can we create procedures in order to find important points on our graphs. There's a lot of information here, but it's all really good stuff. It's all very important. I think this is probably one of my favorite sections in the whole book, so just don't tell the other sections that I said that. So first we're going to start with this theorem right here. It says if f prime of x is greater than 0. So essentially we're saying if the derivative is positive, those are the numbers that are greater than 0, for all points on some interval a, b, then f is increasing on a to b. So let's pick this apart here for a second. F prime, remember that's the derivative. The derivative tells us the slope of the tangent line. So if the slope of the tangent line is positive, so I'm going to draw in a positive line here, or a line with a positive slope. And then I would challenge you to create a function that has this tangent line. So I'm going to create just a couple. So perhaps it looks something like this. And at this point right there, well, yep, my function is increasing at that point, at that particular x value. So okay, maybe we try coming at it from the other direction here. So maybe we look at something like this. And yep, our function is definitely increasing right there at that point. So maybe we try something else. Maybe we try this. Well, it's decreasing right here. So it's decreasing on this little part right here. But at this particular x value, we would say that our function has probably a horizontal tangent line right here. And then after that, and this little section right here, and this little piece that I'm highlighting, our function is increasing. It begins to go up. So yeah, I would say that our function is increasing at this particular point right here where we have our tangent line. Similarly then, if f prime is less than 0, so here if f prime is negative, those are the numbers that are less than 0, for all points on a, b, then f is decreasing on a to b. So I'll draw in a line with a negative slope because that's what the derivative tells me. It tells me slope of the tangent line. And again, no matter how you try to draw your function, right, if I draw a parabola, something like that, at this particular point right here where we have our point or point of intersection between the tangent line and the function, our function is decreasing at that point. And we can try it from another direction. Oops, let's try this. Something like that. And yeah, probably right there, I have a function which is decreasing. So no matter how you draw in a function that has that blue tangent line, it is always going to be decreasing at that point. So this is very cool. I can determine whether a function is increasing or decreasing just by looking at the sign of the derivative. I can actually just look, is the derivative positive or is the derivative negative? And that's going to tell me if my function is increasing or decreasing. So I'm going to use this idea in this first example. I really like problems like this, so I think that problems like this would be good to study if I was preparing for, say, a quiz or an exam. Here I want to sketch the graph of a function f that is continuous on negative infinity to positive infinity and satisfies the following conditions. So here we have f prime of x is less than 0 on a bunch of intervals. We're told f prime of x is greater than 0 on one interval. F prime of 5 is undefined, so f prime of 5 does not exist. And f prime of -1 and f prime of 3 are both 0. So right now we have a lot of information, and I would encourage you to find a way to organize that information in a way that's probably easier to digest, in a way that's easier to understand. I always like using number lines to create to understand exactly what's going on. That's what we're going to be using a lot in this section. So I'm going to create a number line here. And on that number line, I'm going to plot points that I think are important. So points that are endpoints of my interval. So -1, 3, 5, -1, 3, 5, -1, 3. So yeah, those are the only numbers we have. -1, +3, +5. Those seem to be the important points. And what I've done is I've cut this number line up into 4 intervals. And I have these 4 separate intervals. And what I'm going to do is I'm going to look at the information that was given to us, particularly right here in these first 2. And I'm going to look at each interval and determine, hey, is the derivative negative or is the derivative positive? So remember, if f prime is less than 0, here we're talking about f prime is negative. So f prime is negative on -infinity to -1. So that's this interval right here. So I'm going to do a couple things. Here, notice this is a number line for f prime. So I'm going to put a couple of negative signs in there to show that f prime, the derivative, is negative. And we said earlier, hey, if you have a negative derivative, that means that your function is decreasing. So I always like to draw in a little decreasing line there. Helps me remember what's going on. So that was this interval. We're done with that one. 3 to 5. Now we're talking about this interval. So again, between 3 and 5, I have a negative derivative. So I'll put in a few negative signs. And again, just put in a decreasing function just so that I know what's going on. I'm done with that interval. In between 5 and infinity, that's this interval all the way on the right-hand side. And again, I'll put some minus signs there and draw in a decreasing function so that I know what's going on. I'm done with that first condition. Next, f prime of x is greater than 0 on -1 to 3. So when we're talking about the derivative being greater than 0, we're really saying f prime is positive for number 2. So between -1 and 3, that's this interval, the only interval that we have left. We know that our derivative is positive, and if our derivative is positive, our function is increasing. I think that's fairly intuitive once we kind of wrap our heads around that rule. So okay, we're done with that second condition. Conditions 3 and 4, these are a little bit different because they're talking about specific x values rather than points. So for example, in the third condition here, it says f prime of 5 is undefined. So we're talking what's going on exactly at 5. And they tell us that f prime of 5 is undefined. So you can write all sorts of things here. I've seen some textbooks use ND for no derivative because it is undefined at that point. You could actually write in undefined, but I always think that that's kind of wordy and makes it look ugly. Usually what I'll write is I'll say it does not exist. Our derivative does not exist at 5. And the reason I'm doing that is so that when it comes time to actually sketch this part of my graph, I know that the derivative is not defined. So I'm going to have some sort of weird behavior happening for this guy right here. If I think about where or how the derivative might not exist, I could have, say, a sharp corner, whether it's right side up or upside down. I could have a cusp. I could have a discontinuity of some kind, or I could have a vertical tangent. Could be any one of those. So let's hold off on those until later on. We're done with that third condition. The fourth condition says f prime of -1 is the same as f prime of 3, which is 0. So I'm going to put a little 0 above each of those. And this, I think, we're a little bit more familiar with. These, when we say that the derivative is 0, that's when we have that nice horizontal tangent line. And I can actually start to get an idea of what is going on here. I'm just going to look to the left of 5. So if I look at this part right here, I think this part's a little bit easier to look at. So we have, if I were to draw it out right below here, my function is decreasing, so it's going down, it's decreasing. I have a horizontal tangent line, so it needs to kind of level out there for a second. And then after that, it switches to increasing. So now my function is increasing. I see I have a horizontal tangent line again at 3, so I should be leveling out. And then after that, my function is going to be decreasing. And then something weird happens. So I'm actually going to hold off on this. Let's plot what we know, because I think this gives us a really good starting point. Remember that we have these horizontal tangent lines at 3 and at -1. Those are really, really important to include. That is something that we'll be looking out for specifically. So I'm going to put, let's see, -1 and then 1, 2, 3, 4, 5. Now, the y values that you draw these graphs at is not terribly important. You could put this horizontal tangent line, I know that this is occurring at -1. I could put that point down here and say, okay, there's my horizontal tangent line. Or I could put that point up here, there's my horizontal tangent line. As long as it is decreasing on the left and increasing on the right, it doesn't really matter. As long as it's decreasing on the left-hand side, increasing on the right-hand side, and I have that nice horizontal tangent at the bottom of the curve. So let's just leave it something like that. Then after that, my function is increasing until we get to 3. So until we get to 3, so we should have a horizontal tangent line, let's say right around here. So we're going to have a nice kind of smooth top to that curve, and again a horizontal tangent line at 3. And then my function is decreasing. And now we got to talk about the behavior at 5, because this is a little bit different. We kind of said, oh, well, it probably looks like one of these possibilities here. So let's try and rule some of them out. First of all, we'll say, you know what, it can't be discontinuous because it said, hey, it needs to be continuous on -infinity to +infinity. So this is the easiest one to rule out. It can't be discontinuous. So it's not that one. Let's consider the case of a sharp corner. In the case of a sharp corner, my function is decreasing and then increasing, or it's increasing and then decreasing. Both of those are a problem because if I look at my number line, my derivative is negative on the left-hand side and negative on the right-hand side. It's decreasing on both sides. There is no change from increasing to decreasing or vice versa. It's just always decreasing. So it can't be either one of those. For the same reason, it can't be either one of these cusps, because if I look to the left-hand side, if I look on the left-hand side, it's decreasing. On the right-hand side, it's increasing. That means a sign change for my derivative. We just said we don't have that. Same thing with if I flip that upside down, it's increasing and then decreasing. I need it to be decreasing on both sides, so it can't be either one of those. The only thing that remains then is a vertical tangent. I have to have a vertical tangent line. So what's going to happen on my graph over here at this point is my graph is going to have that horizontal tangent line right at 5. And then afterwards it needs to kind of level back out. It's still going to be decreasing, and actually I think I can do a little bit of a better job drawing that in. It's still going to be decreasing after 5, and actually that's not quite there, so let me see if I can try one more time here. Something like this. Hopefully we kind of get the idea. And actually, oops, I don't want it to bounce back up. I want it to continue decreasing. So perhaps we'll just say something like that. So we should see that vertical tangent line right here at 5. I think vertical tangent lines are actually pretty difficult to draw. They're fairly subtle, so they don't need to be perfect. But just know that that's what we're looking for. At x equals 5, I should have a vertical tangent line. So this is cool. We can actually use the sign of the derivative to help us determine whether a function is increasing or decreasing. And actually, we can kind of make a procedure for just that. If I want to determine where my function is increasing or decreasing, I'm going to start by finding the partition numbers of f. So these are values of x where the derivative is either 0 or the derivative is undefined. So this is going to be where my derivative might possibly change sign. The derivative can only change sign if it crosses the x-axis, or perhaps if there's some sort of discontinuity there. So I'm going to try to find those points. Next, I'm going to create a sign chart very similar to what I did in that first example, using the critical numbers. And actually, this is a typo on my part because we haven't defined critical numbers yet. Using the partition numbers to separate the intervals. And then once we have that, we will test a value in each interval by plugging that into f prime of x. So this is a procedure that we'll be using to determine where our function is increasing or decreasing. It's also a procedure that we'll be using quite a bit to help us determine where we have local extrema, as it turns out. So it's a very important procedure. First, here we'll just look at a couple of examples. First up, I have f of x equals negative x to the third over 3 plus x squared over 2 plus 2x. So I need to start, we said, by finding those partition numbers. I want to find places where the derivative is either 0 or the derivative is undefined. So first I need to find the derivative. So f prime of x, this is equal to, let's see, if I multiply the power, I'll cancel that 3, so I'll have negative x squared. Same thing with that middle term, plus x plus 2. So I want to find places where f prime of x is equal to 0, and places where f prime of x is undefined, otherwise known as places where f prime of x does not exist. Let's work with this guy first, because this is going to be the more common scenario that we work with. I'll take my derivative, which is negative x squared plus x plus 2, set it equal to 0, and I'm trying to solve this equation for x. Personally, I never like solving a quadratic equation with a negative leading coefficient, so I'm just going to multiply both sides by negative 1. That will give me x squared minus x minus 2 is equal to 0. And I think that this is a lot easier to work with, because now we can factor. We should be able to factor 2x minus 2 times x plus 1 is equal to 0. So let's see, I will take each factor, set it equal to 0. I should end up with x equals 2 and x equals negative 1. These are two of my partition numbers. So hold on to that thought, because we also need to consider the case where f prime of x does not exist, places where our derivative does not exist. But look at f prime. F prime in this case is a polynomial. So f prime is a polynomial, which means that f prime exists everywhere. Anytime we're working with polynomials, it's nice because we don't really have any extra partition numbers come up with this possibility. But it is somewhat of a double-edged sword, because then it's easy to forget to check the places where f prime of x does not exist if you're only looking at polynomials. So we need to remember to look for places where the derivative does not exist I always try and break it up into these two cases, places where the derivative is 0 and places where the derivative does not exist. I think that it's just a good habit to develop so that we don't ever forget to do that. But I have these 2 points here. I have 2 and I have -1. So my next step, I'm going to create a number line for the first derivative. So I would encourage you to label it as f prime, because later on we'll be creating number lines for the second derivative. I want to be able to keep these things straight. I'm going to put the partition numbers on my number line, so -1 and +2. And we don't necessarily have to do this right now, but I think this is a good habit for what we'll be looking at later. I would also include the behavior of the derivative at each of these values. And to do that, I'm just going to look, well, how did we come up with those? Where did they come from? Well, we took our derivative and set it equal to 0. So I'm going to put a 0 above each one of those. And right now, if we're just solely determining where our function is increasing or decreasing, that part's not important. But eventually we'll be graphing these functions, and we want to know where we have a horizontal tangent line, and these zeros help tremendously. So what I'm going to do is I've really, at this point, I've separated my number line up into 3 different intervals. And I'm going to take a number in each one of these intervals. So I'll take a number here, I'll take a number here, I'll take a number here, plug those into my derivative, f prime of x, and just see whether I end up with a positive result or a negative result. So let's take a number on the left-hand side of -1. How about -2? F prime of -2. Be careful with this minus sign right here. This really says opposite -2 squared plus -2 plus 2. So this will be opposite of +4. These two cancel, so I end up with -4. So what I'm going to do is I'm going to put little minus signs on that sign so that I know that, hey, the first derivative is negative there, so my function must be decreasing on that interval. And then I'm going to repeat this process, now with a number between -1 and +2. So 0 is between those two. I always like to work with 0 whenever I can. F prime of 0, this is opposite 0 squared plus 0 plus 2. So I end up with 0 plus 0 plus 2 gives me 2. So my derivative is +2. It's positive on that interval, which means that my function must be increasing between -1 and +2. Lastly, I need a number that's on the right-hand side of +2, so how about +3? F prime of +3 will be opposite 3 squared plus 3 plus 2. So let's see, this is -9 plus 5. Here I get -4 once again. So my derivative is negative. My function is decreasing on that interval. At this point, all of the hard part of this problem is pretty much over with at this point, because now all I need to do is look at the sign chart that I've created. Look at your number line. Our function is increasing. Our function is increasing wherever we had a positive derivative, so it's increasing in that middle interval between -1 and +2. So when I talk about the intervals where it's increasing, I'll say -1 to 2. I'm using parentheses here to show that, hey, the function is technically neither increasing nor decreasing at -1 and +2. Technically, it's not doing either one of those things. It's constant. And then our function is decreasing wherever we have a negative derivative. So we had a negative derivative on the left-hand interval, which was -∞ to -1, and on the right-hand interval over here from 2 to +∞. So 2 to +∞ there. And there is where my function is increasing and where it is decreasing. So that's very, very cool. We can use the derivative, and I think this process is relatively straightforward. What's nice is we're going to be using it a lot. We're actually going to reuse it for the second derivative too, so we don't have to learn a whole lot of new procedures for these problems. We can kind of keep falling back to this one, and we're going to see it a lot in this section. Let's look at one more here. This time I have x squared minus 2 natural log x. This function's a little bit different than the one that we just worked with, because here, with f of x, we were working with a polynomial. And polynomials have domain of negative infinity to positive infinity. Domain is all real numbers. But in this case, domain of x squared, that's going to be negative infinity to positive infinity as well, so that's fine. But the domain of negative 2 natural log of x, or in particular just that natural log of x, that's perhaps going to be a problem. It's just something that we need to keep in mind. It's not going to make the problem tremendously harder, but it will impact our final answer. And I'm going to make a note off to the side that the domain of this function, because the domain of natural log of x is all positive numbers. So the domain here would be 0 to positive infinity. Not including 0, not including any negative numbers. So I am going to start with my derivative because I need to find the partition numbers first. F prime of x here would be 2x minus 2 over x for the derivative of natural log of x. It's up to you whether you want to leave it like this. Personally, I actually think it's usually easier if we find a common denominator between these two terms. So I'm going to go ahead and find a common denominator. This is really 2x over 1. I'm going to multiply that left-hand term by x over x. And that'll give me 2x squared over x minus 2 over x, which gives me 2x squared minus 2 divided by x. And I think that this makes the derivative actually a lot easier to work with going forward. Because remember, the first thing I want to do is I want to find the partition numbers. I want to find places where f prime of x is equal to 0, and places where f prime of x is undefined, where it does not exist. Well, this rational function that I've created right here, that is only 0 if the numerator is 0. And if you're not sure, if you don't trust me, you can take that whole function and set it equal to 0. The first thing that you'll have to do is multiply both sides by x. In either case, you'll end up with 2x squared minus 2 is equal to 0, because that's the only way that my derivative can be 0, is if the numerator is 0. So I can solve this equation either by factoring or using square roots. Either one will work just fine. I will solve using square roots here. So 2x squared is equal to 2, x squared equals 1. Here x equals plus or minus 1. And the one thing I'm going to check here is I'm going to check the domain of this function. I had -1 and +1. Actually, let's come back to that. Let's come back to the domain in just a little bit. I also care about where is f prime of x not exists here. So in this case, again, I'm dealing with this rational function for my derivative. That's only undefined if the denominator is equal to 0. So here I'll simply just get x equals 0, and that's it. I don't need to solve for anything. So normally, if we model this problem like we did in the last one, we would say, okay, -1, 0, and 1. But there's a slight problem that we have, and it's due to the domain. And that's because some of these points aren't going to make sense to talk about. Because sure, I could take a number over here, and even on this interval too. If I were to take a number in each one of those and plug those into the derivative, I'd be able to tell you whether it's positive or negative. And then you could say, oh, I'm going to make something up. I'm going to say it's positive here, so it's increasing, and then negative here, it's decreasing. But think about the domain. Domain, we said, was 0 to positive infinity only. It doesn't make sense for me to say that my function is increasing or decreasing on those intervals because these are all negative numbers. This interval right here, this is negative infinity to negative 1, and here negative 1 to 0. Those are all negative numbers that we're talking about. So if my function just doesn't exist there, like our domain says it doesn't, then it doesn't make sense for me to say whether my function is increasing or decreasing. So what I'm going to do instead is I'm going to kind of just section off my number line. I'm only going to care about numbers to the right of 0. I don't care about any of this stuff on the left-hand side at all. So really now I just have this one partition number at 1. I'm going to take, let's say, 1/2. We'll plug that into our derivative here. So f prime of 1/2, this is 2 times 1/2 squared minus 2, all divided by 1/2. So let's see, this is 2 times 1/4 minus 2 divided by 1/2, which is really 1/2 minus 2 divided by 1/2. Let's see, this is 3 over 2 divided by 1 over 2 multiplied by the reciprocal, and I'm left with just 3. And really what I care about then is the sign. It's a positive 3, so my function must be increasing on that interval. So okay, I've got that. Next I need to look at, well, what's the behavior over here to the right of positive 1? So I'm going to pick any number that's bigger than 1. How about 2? I'm running out of room here, so we'll say f prime of 2 here. F prime of 2, this is equal to 2 times 2 squared minus 2 all divided by 2. 2 squared would be 4, times 2 is 8 minus 2 over 2. This is really, let's see, 8 minus 2, 6 over 2. This time I get a positive 3 again. What do you know? So my function is increasing as well on the right-hand side of 1. And actually, I've made a mistake, haven't I? Some of you are probably getting ready to email me. Where's my mistake? It was over here. I said 1/2 minus 2 was 3/2, and I was mostly right, but it really should have been a negative 3/2, which means my derivative was actually a negative 3. This is actually pretty darn important. Because what that means then is on that interval I should have had a negative derivative, which means my function is decreasing. That's a pretty big deal. So be careful. As you'll see, it's pretty easy to make a mistake with your signs here, because that's the most important part. That's the thing we're checking for, is we're checking to see, is the derivative positive or is the derivative negative? So just take your time and be careful. The last thing I need to do is just tell whether it's increasing and decreasing. It's increasing where the derivative is positive. So on 1 to infinity, my function is decreasing on this little interval right here between 0 and 1. So this is a really important idea. We're going to be using this a lot even in the next video, the same kind of procedure. As it turns out, we can actually use this to determine where we have local extrema, which is something that we were trying to do back in 4.1. Now we have the tools to go ahead and do that. So we're going to take a look at that and the first derivative test in the next section.